Welcome everyone, and welcome to the second seminar of City-REDI this semester. And today we have Professor Zhifu Mi from UCL to give us talks on the carbon emission accounting of cities. And Professor Mi is a professor of climate change at UCL, and his main research area is carbon footprint, air pollution, and health sharing economy, and climate change assessment model. And he has published in many leading academic journals, including Nature, Energy, Lancet, and Production. And he's the editor-in-chief of the Structure Change and Economic Dynamics, and the editor of Journal of Production. And without further delay, Professor Mi, the floor is all yours.
Thank you. Thank you very much. Thank you for having me here. It's my great honor to be here. And I'm very happy to see my old friend, Yu Li from School of Management and David from Department of Economics. Thank you very much. I'm Zhifu Mi, Professor of Climate Change Economics from University College London. Today I'm talking about the topic carbon emission accounting of cities, because we are a center of city. So my research has several research topics. The first one is carbon accounting. So we develop measures to do the carbon accounting at multi levels, global, national, and city levels. We also investigate carbon emissions from both production and consumption perspectives. So today I'm going to talk about city carbon emissions. I will also introduce the production-based and the consumption-based emission accountings. The measures is used to do the consumption-based accounting is input-output analysis. I'm very happy to know that some colleagues here also use these measures. The second topic is about climate change integrated assessment model. So it's a macro level, global level model to integrate climate change models and economics models. The third topic is about sharing economy. So we would like to explore the environmental impacts of the sharing economy. So we have done some work about the environmental impacts of bike sharing, car sharing, and something like MBB, the hotel, the sharing. So we think the sharing economy has a much potential to promote the sustainability of cities. So this is merely my research. Today I'm going to talk about carbon emissions of cities. Climate change is a typical global issue, but cities are more and more important in mitigating climate change. Cities are the core of climate change mitigation because first, the capacity. Cities cover about only 2% of land, but it has over 50% population, and it contributes to 80% of GDP. So cities are the concentration of people, wealth, resources. So cities have the capacity to do it, have the resources, the money, the technology, and many other things to do it. And the cities also have responsibility. So when we talk about the responsibility of carbon emissions, cities contribute 80% of GDP, also over 80% of greenhouse gas emissions. So cities have the responsibility. The third issue is vulnerability. So in fact, cities are very vulnerable to climate change. So cities are usually allocated by the big river or coastal regions. So when the global sea level rise, the cities will be also very vulnerable. So cities have the capacity, responsibility, and are also have higher vulnerability. So cities should take more actions to mitigate climate change. So the role of cities in mitigating climate change has been changing. So in the past decades, the cities has become faster actors compared to nations. So cities has been developing and implementing key policies on their own. So there's a picture about C40 activity. C40 is a city network. So it covers many cities all over the world. So they aims to take actions at city level. So how to mitigate and adapt to climate change for their own. Another network is ICLER, the Local Government for Sustainability. So it was developed to promote sustainability, but now climate change mitigation has become one of their core activities. So cities are asserting their comparative and competitive advantages to deliver more concrete actions, in many cases, more quickly than nations do. So when we talk about climate change mitigation at the city levels, there are some research knowledge gaps. This is the 4 research gaps summarized in one of our publications several years ago. So the first one is lack of consistent and comparable greenhouse gas emissions at the city level. So this is the topic what we are going to talk today. So before introducing our data, we would like to say that there are mainly 2 measures to account carbon emission of cities: production-based or territorial emissions, and consumption-based emission or carbon footprints. So territorial emissions caused by domestic production together with exports accounts for emissions at the point of production. It excludes the consideration of the final used destination or ultimately used consumers of goods. So it is to account the responsibility of producers. So where carbon is emitted, so the responsibility will be allocated to the producers. By comparisons, carbon footprints, all emissions occurring in the production and distribution sectors are allocated to the final products consumers. So there are a very simple equation between the production-based and consumption-based emission. Production-based emission plus emissions embodied in import minus emissions embodied in export equal to consumption-based emissions. So the gap between the 2 accounting measures is everything okay? Okay, the gap between the 2 accounting measures is caused by the interregional trade. So this is a figure to demonstrate the differences between the measures. Okay, hello? So we can see the production inside the city, the products or services are produced in a city can be used by consumers in the city, as well as the consumers outside the city. In the same way, the consumption inside the city can come from the producers inside the city, as well as the producers outside the city. So if we account carbon emission from producer perspective, so all emissions happened within the city belong to the production-based emission or territorial emissions. So the emissions caused by the final consumption in the city is a carbon footprint or consumption-based emissions. So generally speaking, for most cities, the consumption-based emissions are larger than the production-based emissions. So I will show you some cases in later. So territorial emissions. There are many sources for the territorial emissions. In our research, we mainly focus on 2 sources. The first is fossil energy use. The second is industrial process. The fossil fuel related CO2 emissions mainly come from coal, oil, and natural gas. The combustion of this fossil energy. And we can also allocate the production-based emission according to sectors: the agricultural sector, industrial sector, construction, services sectors. The process related CO2 emissions. These emissions are caused by the technical process rather than the combustion of energy. So there are several processes we considered. One of the most important is the cement production. The cement production contributes a large portion to the global greenhouse gas emission. So how to account the emission? So the accounting of CO2 emissions is different from the accounting of the other air pollutants. So we usually use the energy consumption times a factor called emission factors to get the CO2 emissions. The D fossil is the consumption, is the energy consumption, is in physical unit, and N times H times O is the emission factors. So emission factors are carbon emission emitted in using 1 unit of fossil energy. So we usually, of course, for different fuel type, we have different emission factors. So coal, oil, gas, they have different emission factors, and the coal can also be further divided into different core products. So this is the calculation of the fossil fuel related CO2 emissions. So you can see that emission factors are very important in this accounting. So carbon emissions have a large uncertainty. One of the main reasons is due to the emission factors. So it is impossible for us to know the real emission factors for each coal, each oil, and each natural gas. We usually use a default values to calculate the carbon emissions. So emission factors can cause uncertainty to the carbon emission accounting. For the process-related emissions, so we use D times E. D is the production of amount in physical unit, and E is also emission factor. It represents the CO2 emit when producing unit of industrial products. For example, we have the emission factor for cement. So 1 unit of cement is produced, how much CO2 is caused. So we use this emission factor times the production of the cement. So we use these measures to account the carbon emissions of Chinese cities. So we do it in over 100 cities. We find that, first of all, the emissions are allocated unequally. So the top 5 emitting cities, you might be not familiar from them: Tangshan, Shanghai, Suzhou, Nanyang, and Chongqing. These 5 cities accounted for 11% of the total emissions. And the carbon emission intensity is very different. The carbon emission intensity means the carbon emission divided by GDP. So the carbon emission per unit of GDP. So in Shenzhen, you might know Shenzhen is a very developed city, very near Hong Kong. So Shenzhen, it is only 0.04 tons per unit of 1,000 Chinese yuan. So in Hegang, it is a city, a small city in northeast China. So the city is mainly to produce the heavy industry, to produce a steel or something like this. So the carbon emission intensity is 1.72 tons per unit of 1,000 Chinese yuan. So the gap is about 50 times. So this is due to the development level, the resources, and their industrial structure. Many reasons for this. So if we look at the sectors of cities, we find that first of all, industry makes a very large contribution to the CO2 emission. 87% of emissions from the industry. If we look at the industry further, we find that the power and heat and the air and steel production, some sectors make a large contribution. If we look at the fuel the fuel type, we find that because this is the data from China, we find the main source is from coal, and about 74% is from the burning of coal. So this is determined by the energy mix of Chinese cities. So we divided the cities into 5 types: service-based cities, high technology cities, light manufacturing cities, heavy manufacturing cities, and energy production cities. So we use different color to show the different type of cities. We find that for the service-based cities and high-tech technology cities, they have a relatively low carbon emission intensity. But we find that they still need energy input. They are usually energy production cities around which is very nearby to the service-based city or high technology cities. So this production-based cities can provide energy to these cities. For example, you can see this part. This is the Shanxi Neimenggu. This is a coal production base. So it can provide energy to Beijing, the capital of China. And this region, you might know, here is Shanghai, one of the most developed cities in China. And there is also a coal production base here. So it can provide the energy to Shanghai. And here is Shenzhen, Hong Kong is here. So Shenzhen, Hong Kong. So there's a more oil base. So it can provide energy to Shenzhen. So different cities have their different rules. So we find that some cities might depend on their service sector or high technology sector. They do not produce much fossil fuel, but they need to use energy from other cities. So we look at further the industrial sectors of these cities. So we have 182 cities, and each city have 39 sectors. So we have about 7,098 industrial city sectors. So we find that the top 2.5 of all industrial city sectors per industrial output emissions contribute 30% of the total CO2 emissions. So if the country wants to reduce the emissions of those cities, so if we can pay attention to a very small number of cities. So if these cities can reduce their carbon emissions, the total emissions will be reduced by a very large proportion. So this is that the differences between the cities are very large. So consumption-based emission or carbon footprints. So how to calculate the carbon footprints? So for production-based emission, it's relatively simple. We just use the fossil energy use times the emission factors, or industrial process times the emission factors. We can get the territorial emissions. For the consumption-based emission or carbon footprint, we need to use the input-output analysis, the environmentally extended input-output analysis. It is an approach to estimate the linkages between economic activities and environmental impacts. So based on these measures, we can estimate the carbon emissions of a city from consumer perspective. So these are two basic equations for the input-output analysis. I'm not going to talk about the details of these measures. I would like to introduce how this measures is used to calculate the carbon footprint. So this is my iPhone XS with 64 GB memory. To produce this iPhone, we need to emit about 70 kg CO2. So 70 kg CO2. So I would like to use this case to know every consumption in our life will contribute to carbon emission. So what does 70 kg CO2 mean? So the average weight of adults is about 70 kg CO2. So it means that when we use this iPhone, so we contribute to the CO2, which is very similar to our weight. It's smaller than my weight. So we need to know this. If this iPhone was produced in China and exported to the UK, so a UK consumer bought and used this iPhone. So this is a trade, international trade. From production-based accounting, this 70 kg CO2 belong to China. So China needs to pay a responsibility because China use energy, emit carbon emissions to produce this iPhone. But from consumer perspective, if consumers are responsible for carbon emissions, this 70 kg CO2 belong to the UK. So these are the two different accounting measures, the territorial emissions and the carbon footprints. So why do we care carbon footprints? So we find that a widened gap between the territorial emissions and carbon footprints in cities with a higher GDP further indicates that the developed cities tend to push production-based emission outside their city boundaries. So the developed city can outsource the heavy industry or high carbon intensity industries to other cities. So, and the gap between the territorial emissions and the carbon footprint, it's become larger. So carbon footprint can avoid a carbon leakage, which is one of type of spillover effect. So what is a carbon leakage? So it refers to the situation that may occur if for some reasons of cost related to climate policy, businesses were to transfer production to other countries with lesser emissions constraints. So this could lead to an increase in their total emissions. So carbon leakage has become a very serious issues to affect our climate change mitigation effectiveness. I would like to give an example. So if we have two cities, city A and city B, both cities need 10 iPhone. So city A need produce iPhones, 10 iPhone and emit 1,000 kg CO2. And city B produce 10 iPhone and emit only 500 kg CO2. Maybe city B is more developed, has better technology, has good energy structure, something like this. So the carbon intensity to produce the iPhone in city is smaller than that in city A. So now the city B want to reduce carbon emission. So the city B produced a more strict climate policies. It means that the costs to produce iPhone is much higher in city B. So the city B, the producers of iPhone in city B can only produce 5 iPhones because the producers lost their competitive advantages. So, but the city B still needs 10 iPhones. So the city A can make response. The city A produce 5 iPhone more and export 5 iPhone to city B. So the city B emissions is reduced. So this is the target of city B. So city B want to reduce the carbon emission. But the result is that the carbon emission in city A is increased. So the total emissions between the cities become 1,750 kg CO2. So which is higher than the original total carbon emissions. So this is a very tricky issue. City B wants to do something well. So City B wants to reduce carbon emission, but the results are that the total emissions are increased. So this is the carbon leakage. This is the carbon leakage. So if we use carbon footprints, if we do not care where the iPhone was produced, we only care if we care about the where the iPhone is consumed. So if we use the carbon footprint, it can be excuse me, it can be used to avoid this kind of issue. And you know, the European is talking about the CBAM, the carbon border adjustment mechanism. The CBAM is also one solution to resolve this problem. So CBAM is designed to avoid the carbon leakage. So we use the environmental extended input-output analysis to estimate the carbon footprints of Chinese cities. So this is the 11 cities. We find, you know, the carbon footprints from a city can be divided into two parts. The carbon emissions emitted in the city and used in the city, and also the carbon emissions embodied in their import. So we find that for most of cities, the emissions from the import products are higher than the emissions of products produced within the city. So for Shanghai, Beijing, these mega cities, the over 70% of CO2 are imported from other regions. So I think the proportion for London, this kind of the mega cities, it should be similar. And we can further divide carbon footprint in several categories. So it includes household consumption, government consumption, change in inventories, and capital formation. So it can be consumption and investment. The consumption includes the household consumption and the government consumption. So the Chinese cities, we can see the most proportion is from the investment, is the capital formation. So this is determined by the economic pattern in China, because investment, many cities in China is investment induced pattern, but it's different in the UK. So if we look at the carbon footprint of the cities in the UK, we find the consumption, the household consumption makes a very large contributions to the final the carbon footprint. So by comparing these 11 cities, we find that with the development of economy, some cities tend to change from production-based pattern to consumption-based pattern. So at the beginning, a city might need to develop their economy. They need to use plenty of the fossil energy, and they emit CO2 emission. So their production-based emission are higher than the consumption-based emission. But with the economic development, they might have higher environmental cost, higher labor cost. So they find they need to the more clean air, clean water. So they become a consumption-based pattern city. So it means that their production-based emissions are smaller than their consumption-based emissions. So for most of cities, they have this kind of the pattern. So it means that we can imagine that so more and more cities become consumption-based emission. Their consumption-based emissions are higher than their production-based emissions. So who will produce the products? So it means that with the development, a city or a country will outsource more and more heavy industry or high carbon intensity industry to other regions. So in China, we find that these developed cities are outsourcing their carbon emissions to the less developed cities, to the western regions. You know, China, the West China and East China. The East China is much more developed. So the cities with better development are outsourcing their emissions to the Western China. So it means that the consumption in one city can induce carbon emissions outside the city. So if we want to mitigate climate change, the collaboration, the cooperation between the producing cities and consuming cities are very important. So the last topic I would like to introduce is a new measures to estimate the carbon footprint. So we talk about why we want to use carbon footprint, but when we try to use carbon footprint to do analysis, we find a very serious issue is that we are lack of data. To estimate the carbon footprint, we need to have the territorial emissions and input-output tables. But both of the data are very limited at the city level. For example, there are 3 widely used carbon footprints, city carbon footprints results. So they have very serious time lag. So the first one is 5-year lag. So the paper was published in 2018, and the data is for 2030. And this paper was published in the 2014, and the data is for the 2001. So there are very serious time lag in the estimation. So we will want to estimate the carbon. We want to do some analysis of carbon footprint of cities. We cannot find the latest data, and they are very good. The database is a carbon. It is called Carbon Monitor. It can provide nearly real time the data, but it only includes the scope 1 and scope 2 emissions. So for carbon accounting, we have a scope 3, scope 1, scope 2, and scope 3 emissions. So if we want to calculate the carbon footprints, we need to have some scope 1 and both scope 2 and scope 3 emissions. So scope 1 emissions are the emissions emitted within the city. Scope 2 is the emissions caused by the electricity imported to the city. And scope 3 are emissions caused by the other products imported to the city. So this database is very good. It's near real-time estimation, but it does not have the scope 3 emissions. So we proposed a new measures. It used the crowdsourced data to estimate the carbon footprint. So it is an integration between the bottom-up and top-down measures. So the carbon footprint here is defined as the carbon dioxide emissions embodied in production of goods and services consumed by the residents, government, and capital investment within the city. So this is the carbon footprint. So this measures mainly includes two parts. The first part is top-down measures. It's a national level input-output analysis. So it is using the Excel-based MRRO table. So it can give us the national carbon footprints. So national carbon footprint, it can be divided into household carbon footprint and non-household carbon footprints. So this is the top-down measures. So we have assumption that because the carbon footprint is mainly caused the consumption level. So we assume that the carbon footprint is positively correlated to the purchasing power. Purchasing power is income times population. So we do not have the purchase power data. So we use a crowdsourced database. So it's a website. Each users can log in the website, can provide that consumption information. How much you spend in food, how much you spend in travel, how much you spend in your house, and how much you spend in your education. So each one can provide that consumption data in the website. And it's a big data. So we use this data, crowdsourced data, to estimate the purchasing power of a city and use it as an indicator to estimate the carbon footprint. So the website is called the NumView. If you are interested, you can search NumView and look at the website. So each of us can provide our own information on the website. So we use this kind of data to estimate the carbon footprints of cities. So we estimate the carbon footprint of 464 cities. So first of all, we have to admit that there are large uncertainties in this kind of estimate because it's crowdsourced data. So the users might not estimate their own consumption level correctly. And for some cities, the sample are very relatively small. but for some cities, the sample is large. So, but anyway, so we can get the advantage of this method is that we can get more timely data. So this paper was published last year, and our database is for 2020. And we can also provide the data for 2021. So with these measures, so we reduce the time lag from the 5 to even 10 years to 1 or 2 years. So this, we find that this 465 cities contribute to 10% of global population, but they contribute to 18% of global CO2. If we compare the per capita footprint of our sample cities is 8.1 ton, and compared with the global average is 4.5 ton per capita. So based on this figure, so I would like to say that our city sample is biased. We are lack of the small cities or cities from the developing countries. So we have more cities in developed country because, you know, we use the crowdsourced data. So most users for this website are from developed regions. So we can see the CO2, the carbon footprint per capita is higher in our database. So with this database, we did some analysis. First is an equal distribution of carbon footprints. So the top 10 earners of the cities contribute to 25% of emissions, and top 20 earners contribute to 41% CO2 emissions. And the bottom half, the bottom 50% earners only contribute 23% of total emissions. So the carbon footprints are unequally distributed among the cities. So I would like to say that the inequality might be more severe compared to our result, because, you know, our result have less cities from developing countries. If we consider the cities in developing countries, the inequality might be much higher. So we developed a coefficient, a carbon footprint Gini coefficient, to measure the inequality of the carbon footprints. So Gini coefficient, I think you might know that Gini coefficient is used to measure the inequality of income. So it's a number from 0 to 1. 0 is totally unequal, and 1 is a perfect equality. So the carbon footprint Gini coefficient is a similar concept. It's also a figure from 0 to 1. So larger carbon footprint Gini coefficient, the carbon footprint are more unequally distributed. So we find that we divided the cities into developed countries and developing countries. We find that the carbon inequality in developing countries is much higher. If we look at the global cities, the Gini coefficient, the carbon footprint Gini coefficient is smaller than the income Gini coefficient, but the carbon footprint Gini coefficient in developing countries is higher than the Gini coefficient of income in the developing countries. So we find that the disparities within developing countries for carbon footprint are much higher than the income disparities. So we find that the cities in a region show some similarities. So for example, North America cities, North America, you know, the North America cities usually have relative higher carbon footprint per capita. So this is determined by their lifestyle, by their consuming products. So they have very energy intensive lifestyle. So for other cities, we can see the European cities. European cities have relatively low carbon footprint per capita. So this is merely due to the strict policy and advanced technology. So the highest carbon footprint per capita is from the Middle East cities. This is because of their reliance on the fossil energy consumption. If we look at other cities, the cities in Africa or cities in India, so we can see their carbon footprint per capita is also relatively lower, but the reasons are different from that in the European. In the EU, the carbon footprint per capita is relatively low because they have the strict policy. The carbon intensity of products in the EU is relatively lower. But the reasons for Africa or India is because their consumption level is relatively low. So the carbon intensity in these regions are relatively high, but because the economic development level is lower compared to European and North America, North Africa, so they have a relative lower household consumption level. So this is why their carbon footprint per capita is also relatively low. So we want to test two effects for the carbon footprints. You know, when people analyze how to reduce the carbon footprints of a city, so they proposed two effects. The first effect is scale effect. Scale effect, it means that economies in scale in the provision of goods and services may result in higher energy efficiency, and there is a low, and therefore a lower carbon footprint per capita in larger cities. So this is the effect, a scale effect. But according to our database, we find that there are no significant relationship between the population and the carbon footprint per capita. So the scale effect is not tested in our database, but I want to say that our database has bias because we do not have, we are lack of the cities in developing regions, and we are lack of the smaller cities. So, but according to our cities, we cannot find the scale effect for the carbon footprint. The second effect is density effect. Density effect, it is that a city with a higher population density can increase resources efficiency and thus reduce direct emissions per capita. So density more significantly affect the indirect emissions via high income in density in these cities. So what does it mean? So if we look at these three figures, so it shows the horizontal axis is population density, is the people per square meter, per square kilometer. The vertical axis is the carbon footprint per capita. We find a positive correlation between the population density and carbon footprint per capita. So it means that when the population density is higher, the cities tend to have higher carbon footprints. So it's not the density effect. So according to density effect, when population density is higher, the carbon footprint per capita should be smaller. But our result shows the positive correlation. So we are thinking about the reason behind this. So we find that compared to the density effect or scale effect, some economic factors might be more important in determining the carbon footprint of cities. So as we estimate the carbon emissions from the consumer perspective, so the consumption level or the purchasing power of the city are more important to determine the carbon footprints of the cities. So we also look at the inequality of the cities, this global 465 cities. So we make three scenarios. So if the super empty cities reduce carbon footprints, so what will happen? So three scenarios. The first scenario is that all the above average emitters reduce their carbon footprints to the global level, average level. And the second scenario is cities with the carbon footprint higher than 1 standard deviation reduce their carbon footprints to the global level. And the third scenario is cities with higher, I'm going to finish in 3 minutes. With higher carbon footprints, 2 standard deviations reduce their carbon footprints to global level. We find that for the third scenario, the cities with 4% of total emissions can reduce 11% of the total carbon emissions. So the limited number of cities, if they take action to reduce their carbon footprints, it will make a large contribution to the global carbon footprints. So let's summarize what I just introduced. First of all, the more affluent cities usually have systematically lower emission per capita, emission per unit of GDP. It is supported by the imports from less affluent industrial cities located nearby. So city consumption induces carbon footprints in other regions. So the cooperation between producing cities and the consuming cities is critical to mitigate climate change. The consumption-based accounting can be a complementary tool. So we are not going to say that we have to or we only use consumption-based emission accounting. So we are proposing that we use both production-based emission and consumption-based emission. So we integrated the 2 measures to allocate the carbon emission responsibility and to take the relative climate policies. Secondly, we developed a hybrid measure. It integrated the top-down input-output analysis and bottom-up crowdsourced data to estimate the carbon footprints of global cities. So this measure can reduce the time lag of such assessment greatly from 5 to 13 years to 1 or 2 years. So this measure, so we admit that these measures still have many problems, still have large uncertainties in estimating carbon footprint. But we think these measures will be more valuable with the development of big data technologies in the future. You know, we are entering a digital society. So with the development of the digital technology and the internet and the smartphone or like this, so in the future, we can have more high quality, the crowdsourced data. So with this kind of data, we can give more timely and more accurate carbon footprint estimate of cities. So yeah, that's all. Thank you very much.
Thank you very much for this exciting talk. So we have about 12 minutes left for questions. Just wondering if there are any questions from the audience in the room.
Thank you very much, Professor Mi. Can I ask that in your first part, you introduced the coefficient for carbon emission from different sectors.
Yeah.
I believe that this coefficient going to affect a lot on your final calculation result. How do you ensure that this coefficient number is accurate?
You mean the first part of the production-based emission?
Yeah. That question.
Is this
Previous.
this one?
Yeah, I think this is the result, but in your equation, you have a.
You mean here? Yeah. Very good question. So it's very difficult to say which emission factors are more accurate or which emission factors can provide more real estimation. So as I introduced, the emission factors can bring very large uncertainties to carbon emission accounting estimation. So the most widely used emission factors is from the IPCC report. The IPCC has published a national inventory guidelines. So they provide the default value for the emission factors for each type of the field type. So, you know, how did we get the emission factors? We usually do the lab experience to lab experiments to get the real data. But the problem is that, for example, for coal, we use the emission factors is large different for the coal produced in different places. So it is impossible for the IPCC to provide the accurate emission factors for each region. So they just provide an average default value globally. So the more accurate measures to get the emission factor is to do the lab experiments for each local. So for example, in 2017 or 14, a paper published in Nature is about the carbon emission factors of China. So they did plenty of the lab experiments to check the carbon emissions of coal. They find that the default value of IPCC report is highly overestimated the carbon emissions of China's coal consumption. So this is one of the way to know the more accurate emission factors. So the main uncertainty is from the emission factors. Yeah, many thanks. Yes, yes.
When you talk about scale effect and scale effect and intensity effect, I was wondering the third one you mentioned about non-struct, is that similar to the composition effect?
What is the third one?
The third one you mentioned, it is not it should be the economic structure. Like, so is it like the composition effect?
Yeah, so you know, here we tested the scale effect and the density effect. So we find that either density effect or scale effect can reduce carbon footprint when the cities develop, when the city is becoming larger. So we find that the more important reasons or more important effect is from some economic factors such as consumption and such as the household expenditure levels. So compared to the scale effect and the density effect, the economic factors, the consumptions are more important. So this is what I want to say. Yeah. Thank you.
I have two questions from online from Sam Sales Organization. The first one is how can we set boundaries for territorial emission scope 3 emissions upstream and downstream?
Mm-hmm.
And the second one, I think actually echoes you question about which is I heard lots of estimations, so we have also an estimation of data accuracy and the trust.
Mm-hmm. Yeah, thank you very much. So this is a very good question. So I would like to do I have a neighbor to write them? No. So yeah. So the scope of the boundaries of the scope 3 emissions I need to introduce, because due to the limited time, I did not introduce what is the scope 3 emissions. So for emissions, we have scope 1, scope 2, and scope 3 emissions. So what is scope 1 emissions? For a city, the emissions emitted within the city boundary is the scope 1 emission. Scope 2 and scope 3 are, the scope 1 is direct emissions. Scope 2 and scope 3 are indirect emissions. The scope 2 emissions are the emissions embodied in electricity or heating. For example, if the Birmingham city used electricity or heating produced outside the Birmingham, so this part is the scope 2 emissions. Scope 3 emissions, it has much larger boundaries. So all the products or services produced outside the Birmingham and used in Birmingham will be the scope 3. All other indirect emissions. So all other indirect emissions are scope 3 emissions. So the question is very good, is ask the boundaries of the scope 3 emissions. So this is a very difficult question because it's very difficult to define the boundaries of the indirect emissions. In our research, the good thing that we use input-output analysis. With the input-output analysis, so our equation is C equal to E times I minus A inverse times Y. So Y is the consumption. So in the input-output analysis, I minus A inverse is called the Liang-Tibby inverse. So this inverse can tell us the output induced by the consumption along the whole supply chain. So the E is the carbon emission intensity. So with the environmentally extended input-output analysis, we can calculate the carbon footprint caused by the all final consumption. So in the input-output analysis, we do not consider the boundary issues because for the input-output model, we assume that all the productions belongs to one kind of the sectors, which can be described in the input-output table. I think this question, the boundaries of the scope 3 is merely for example for one city. If we want to estimate the carbon footprint of one single city, and we do not have the input-output table, so it will be more difficult here. So the question is merely for this kind of situation. So we need to give some boundaries. So where we will start, where we will start, what kind of products we will consider. So, oh, I'm sorry. I think the people online cannot see my whiteboard. Apologize. Okay, so the second question is, I hear lots of estimation. Do we have also an estimation of data accuracy and trust? Yes, we do. For our data, for example, for this measure, because this is a new proposed measure, and the data we have uncertainty in the data, we compare our database with other database because we cannot find any other database with also so latest with our database, but we have some database many years ago. So we made assumption that if because we have the GDP growth for these cities. So for example, this database is 2001. So we assume that in the past 20 years, if their carbon footprints increase with the same rate with their GDP growth, so how much their carbon footprint will be. So we compare these three databases with our databases. So we find that the gap between our database and their databases is acceptable. So we have shared our data here. So if you go to this big share, so you can find the carbon footprint database of all our 465 cities. So you can use it. Of course, if you find any problems, you are welcome to contact me. This is a very early version of this proposed method. So our idea is that in the future, we need to use the digital technology. We need to use big data technology to estimate our carbon footprint. Thank you for coming. Thank you. Yeah, thank you.
Thank you.
We can go back to the example you showed an iPhone City-A, City-D.
Yeah,
I mean, in my opinion, I'm very critical that you consider the initiative in the user side. But this approach, do you think may bring some negative effect? For example, the total requirement item may drop from 20 to 15, which is good for carbon emission clearly, but bad for economy.
yes, I agree with you. This is, yeah, so as I said before, I'm not going to say that we need to use consumption-based carbon accounting only. So we propose that we use both measures. So if we only use consumption-based accounting, it will bring some negative effect. So our idea is that we use both of accounting because, you know, no matter for international climate negotiation and in domestic climate policy, almost all the policies are focused on the production-based emission. So this is why carbon leakage happens. And this is why the EU wants to propose the carbon border adjustment mechanism to avoid the carbon leakage. If we consider using consumption-based emission as well as the production-based emission, we use the two measures together, it will might be better to resolve this problem, especially the carbon leakage. Yeah.
Thank you. I think we run out of time. Thank you very much for coming in.
Thank you.